In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself, Pranav, is here to deliver today's presentation, Power Transformer Part 13. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with effect of bar formation. During a specific code building process, by means of slitting, cutting, and punching from large, thin electrical steel sheets, there would have been a possibility of some unwarranted fragments of material called bars, which remain attached on the edges of electrical steel laminations. For very precise cutting of thin electrical steel coils into narrower width coils, slitting operations are used as the applied processes are continuously fast, totally automated, and very economical. To have a final shape for slitting is often supplemented by punching of holes in the laminations to operate as location guides for use during core assembly or as cooling ducts in the final core assembly. Bars usually occur during cutting processes as a sharp curved edge, which are of the much importance because they may have to worsen the stacking factor as well as can have a cause to instigate short circuits between adjacent laminations, which in turn increases the core loss. Again, I repeat, bars usually occur during cutting processes as a sharp curved edge, which are of much importance because they may have to worsen the stacking factor as well as can have a cause to instigate short circuits between adjacent laminations, which in turn increases the core loss. Now see the picture, how to slit the electrical steel sheets. Beyond the desired machined features, if those undesired projected edges are of dimensions equal or greater than the thickness of insulating coating of grain-oriented electrical steel, that is 2 to 5 microns, then there may have to create electrical connections between adjacent steel laminations when are stacked on top of each other and between two consecutive turns of a strip in a wound core. The main parameter of a bar on the edge of an electrical steel sheet is its height, and that is not to exceed 0.025 millimeter according to EN 10107-2005. Such occurrence of electrical contact between the laminations allows eddy currents to flow between the two laminations within the large short-circuited area, as well as between the two different short-circuited areas. As the stacking factor of the core refers to the thickness of the laminations in the core, it is then to be decided also by the insulation coating thickness of the respective laminations and the bar height. Therefore, lower be the bar height, higher will be the stacking factor of the core. Higher the stacking factor of laminations, which may be about 0.97 to 0.98, higher is the core area obtained, which leads to a more cost-effective design. Any accidental damage of insulation coating of electrical steel laminations as due to burrs can cause electrical contact over a large surface area, resulting flow of eddy currents over a large core volume. However, burrs can be removed by passing the laminations through a deburring process. Any undesired scratches developed at the edges during the deburring process, then affected area is better to cover up by applying a thin coat of varnish. With more emphasis on bar height and bar thickness, the manufacturers have much concerned in determining the optimal levels of the process parameters, including the tool property, tool geometry, tool edge configuration, properties of the electric steel material, etc. All these factors are found to be responsible for bar formations. Now see the sheared zone and the trimming zone as well as shearing. You just see the rollover portion, the sheared zone portion, then the fractured zone portion, again the bar formation zone. Now see the fracture angle. Since bar formation is a complicated phenomenon and its formation involves significant effect on core manufacturing process, so much more advanced machining technology is there to be configured depending on the crystalline structure and temperature behavior of the subjective grain-oriented steel material. When evaluating the effects of bars for the formation of the lamination edge, another important aspect that has come into effect as the stress zone created at the cut edge. This stress, which is introduced to the steel up to some distance from the cut edge of the sheet, has ultimately forced to degrade the electromagnetic properties of the electric steel. It affects permeability, losses, flux distribution, BH loop, and magnetostriction of the metal or the material. However, some of the magnetic properties can be recovered by the process of stress relief annealing applied to the laminations at a temperature of about 800 degrees centigrade under inert gas atmosphere, but affecting properties can never be fully restored. Abnormality of flux density would have been caused not only by the formation of bars, but also by the defects or distortion of crystal structure in the steel sheet, or due to certain specific design criteria of the laminations, such as at regions in the corners and T-joints, as well as bolt holes, where the flux tends to move away from the rolling direction and intends to have changes in flux density at that particular region. Physical configuration of three-phase core-type transformer. The cores of three-phases transformers are placed in 120-degree phase shift to each other, and if a balanced three-phase sinusoidal voltages are applied in their windings, then their corresponding fluxes phi1, phi2, phi3 will also be in sinusoidal and balanced. As convention, sum of the currents in phases is 0. As convention, sum of the currents in phases is 0. Therefore, center leg as being combination of three core limbs will carry the sum of all the fluxes. That is, phi equals to phi 1 plus phi 2 plus phi 3 equals to 0. Hence, it can be concluded that to remove the central leg has made no difference for other transformer conditions, and the core arrangements of the three-phase transformer is therefore be made with three limbs in the same plane. Again, I repeat. Hence, it can be concluded that to remove the central leg as has no difference for transformer other conditions, and the core arrangements of the three-phase transformer is therefore be made with three limbs in the same plane. This can be built with two numbers of IAC and to hold the three core limbs. See the diagram. Constructional features of shell-type transformer. In a shell-type transformer, the magnetic circuit, that is, the iron core, has to form a shell surrounding the windings. Thus, the core encircles the winding and the flux as produced in the central limb divides equally and returns through the outer legs. In core-type formation, the magnetic flux flow paths on both left and right extremes may have to use the external tank walls and the insulating medium for their return paths. So, a certain percentage of the magnetic lines of force has always to flow outside of the core, which denotes as leakage flux. Whereas in case of shell-type transformer, the magnetic flux as shown external to the coils on both left and right extremes has completed its path for stray and zero sequence flux to return to the coils through core. See the figure 50. Therefore, possibility of leakage flux would have been more or less nil. See the diagram. One is core-type transformer, another is shell-type transformer, three-phase. The flux linking right side and left side in core-type transformer is just outside. That is, it flows through the tank cover. In case of shell-type, see the flux totally within the core. Left side and right side core limbs. HV and LV winding are wound on central limb, and the two outer limbs complete the low reluctance flux path. See the schematic diagram of the three-phase shell-type transformer. Now, three-phase transformer with shell-type core construction consists of 5 limbs where the core surrounds the windings made on the 3 limbs, and other 2 limbs, extreme right and left limbs, hold the 3 limbs as a single unit and also provides a return path for the fluxes. The constructional structure is similar when 3 single-phase transformers put side by side, whose each phase has its independent magnetic circuit and return path for flux. As compared to core-type structure, 3 phases are more independent in shell type construction. As compared to core type structure, three phases are more independent in shell type construction. Configured with HV-LV windings, the entire core structure is placed inside the transformer tank filled with oil or for cooling. As per requisite, winding connections of the three phases would have to be made inside the transformer tank, and the HV and LV terminals of three phases are taken out of the tank through bushings for external connections. Comparative study of core type and shell type transformers. Features, constructional features. In core type transformer, it is much simpler in design and permit easier assembly and insulation of winding. Whereas shell type transformer, it is complicated in every respect. Mechanical forces. Number one, forces as produced between HV and LV windings in case of core type transformer is proportional to the product of the currents carried by them. In core type transformer, number two, very large electromagnetic forces are imposed when LV winding is short-circuited. Since the windings carry currents in opposite direction, so a force of repulsion exists between them. LV winding experiences a compressive force and HV winding experiences a tensile force. Number three, windings have poorer capability of withstanding electromagnetic forces. Whereas shell type transformer windings have greater capability of withstanding electromagnetic forces as produced under short circuit, since windings are surrounded as well as supported by the core. Leakage reactance. In case of core type transformer, large space required between the HV and LV winding. It is not possible to subdivide the windings, so leakage current and leakage reactance is comparatively higher. Whereas in shell type transformer, windings can be easily subdivided by using sandwich coil. So it is possible to reduce the leakage reactance. Repairing job. In case of core type transformer, number one, as the winding is completely accessible, so coils can be easily inspected. Number two, in core type transformer is easy to dismantle for repair. For shell type transformer, as the coils are surrounded by core, so it is rather much difficult in inspection and repair of coils. Cooling facility. As windings are exposed, so better cooling is possible in winding than core. Whereas shell type transformer, as the core is exposed, so better cooling is possible in core than winding. Extra high voltage situation has longer mean length of core and shorter mean length of coil turn. Hence, suitable for extra high voltage requirement. In case of shell type transformer, it is not at all suitable for extra high voltage requirement. Connecting the windings of a three-phase transformer. For transformation of three-phase voltages, the most commonly used three-phase transformer winding connections are star-star, delta to delta, star to delta, or delta to star. The transformer as deployed for power generation and distribution network are mostly of three-phase system, and that could be constructed either as a bank of three independent identical single-phase transformers, or could be single three-phase transformer with a single three-legged core. While a three-phase transformer would have been built by suitably connecting three single-phase transformers with having same ratings and operating characteristics, then any fault occurs in any one of the transformers, the system can still be retained at reduced capacity by the remaining two healthy transformers with open delta connection. See the connections diagram. Star star, delta delta, star delta, delta star. Criticality in selection of winding combination. Transformer winding connection of any one combination, either star star, delta delta, star delta, or delta star, has an immense impact on the major setup with the criticality of system network. Preference of star-star connection is normally not to be considered for higher voltage system. Again, I repeat, preference of star-star connection is normally not to be considered for higher voltage system, as because there is an instability of neutral during the unbalanced loading conditions, and also having the major interference of the third harmonic components. As the zero sequence current flows through the transformer, so it has every possibility to have a different loading in phases, causing to an unbalanced high voltage system. Transformer with star ground connections, there might have been a chance of tripping through differential relay as because of external line to ground faults. Such situation may have to arise while the neutral connection would allow the fault current back in. Then in a differential protection zone where the current entering is not the same as current leaving, and therefore relay will actuate. To eliminate the third harmonic current in the external circuit, it is being well suggested to have at least one delta connected winding in a three-phase transformer. It is therefore star delta and delta star connections are always preferable to transformers in high voltage systems. The star delta connections are being used for stepping down voltage, whereas delta star connections are used for stepping up the voltage. Again, I repeat, star delta connection are being used for stepping down the voltage, whereas delta star connections are used for stepping up the voltage. In both the cases, the delta winding has to trap the zero sequence current. But in a delta connection, as the line and phase voltages are same, hence more insulation is required for individual phases, and that leads to higher overall cost of the transformer. The delta connection in star delta and delta star must have to assure balanced voltage on the star side and has to provide a path to flow the third harmonics and their multiples without using neutral wire. By applying this concept, an additional delta winding is designed to place in the star-star primary and secondary winding, which is known as tertiary winding. Therefore, the entire system will then be confined within the best possible configuration of star delta star system having no provision of neutral wear. Let's stop here. Further to be continued in later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you.